Hello, friends. This is Jim here with Science Talk. And just saw this abstract for a paper that's going to be being published later on. But kind of interesting here. So it will appear in Geophysical Research Letters. It's Nicole Shibley and Mary Louise Timmermans. And the title of their paper is The Beaufort Gyre's Diffusive Staircase Fine Scale Signatures of Gyre Scale Transport. What are they talking about? Take a look at the abstract. The Arctic Ocean waters sourced from the Atlantic contain a vast amount of heat. Right? We've established that. In the Arctic's Beaufort Gyre. Now, the Beaufort Gyre is basically in the Beaufort Sea, kind of Beaufort Sea, Chukchi Sea area. It is anticyclonic, so it's a clockwise flow. Diffusive convection is the primary mechanism by which this heat is transported vertically. Now, keep in mind, the Atlantic water that comes in there is the intermediate water. It's warm, but it has a higher salinity, so it sinks to intermediate depth. So it's actually coming in under the surface layers. And as we discussed, that heat eventually diffuses upward to prevent the sea ice from forming, melted early in the year. When there is no sea ice, that heat diffuses to the atmosphere. Well, the water is also mixing vertically. And that's what they're looking at here. The mixing process is characterized by a quote unquote staircase where convective layers are separated by interfaces in temperature and salinity. Translation: density differences. It is not well understood what governs layer thickness. That's true, which is an important parameter in heat transport. Also true. Here we relate staircase properties to the background water mass structure of the Beaufort Gyre via analyses of ice tether profiler observations. We find that staircase layer thicknesses vary with intrusive features below the staircase and the stratification overlying the staircase. We relate these features to the pathways of anomalously warm Atlantic water in the Beaufort Gyre. So basically what they're implying there is that warm Atlantic water, in addition to swinging around on the Eurasian side of the Arctic Ocean, is somehow getting entrained within the Beaufort Gyre. Results suggest that intrusive features and context of the gyre's large-scale geostrophic flow may be key to understanding layer thicknesses and propagation of warm waters into the gyre. Propagation of warm waters into the gyre. That's kind of a key aspect to this work here. Now, geostrophic flow is just basically a flow due to differing levels of the sea height that creates a pressure differential, that creates a pressure gradient. Water flows down the pressure gradients acted upon by Coriolis, which we're close to the North Pole. Coriolis is going to be most pronounced at latitudes near the North Pole. So, that's what they're getting at there. Okay, so what do they say in the key points here? Atlantic water layer diffusive convective staircases in the Beaufort Gyre exhibit a west to east gradient in layer thicknesses. Layer thicknesses are correlated with the stratification overlying and intrusive features surrounding the Atlantic water core. This layer thickness gradient may be due to lateral propagation of a warm Atlantic water pulse that entered the Central Arctic in the 2000s. Okay, I would not call the flow of warm Atlantic water into, okay, I don't know why I was doing that. I would not call this flow of warm Atlantic water a pulse. It's been steady. So, not the best choice of word there. So, what's the plain language summary? Heat from a warm Arctic Ocean water layer, known as the Atlantic water layer, is vertically transported by double diffusive convection. This process frequently is evidenced by a staircase structure, which basically means it's done in steps, hence the differing layers that they alluded to earlier. We relate changes in staircase properties to both the background oceanographic setting as well as to an anomalously warm water pulse which entered the Arctic Ocean in the 1990s to 2000s. Well, okay, so now seeing this context here, maybe back in the 1990s, 2000, that might have been considered a pulse, but now we know it's a regular feature, all this warm Atlantic water that continuously flow into the Arctic Ocean through the Fram. We show that staircase properties are likely related to the propagation of warm water intrusions and subsequent dissipation of their property gradients. This work sheds light on what the Western Arctic Ocean may look like under continued climate change. Okay, so they're talking about you got the Atlantic water coming in, flows around the Eurasian side, as it swings around towards basically the Bering Strait. Okay, it's probably getting picked up or mixing influence with the Beaufort Gyre that is rotating approximately in that location, and then it entrains that water into the Gyre. Keep in mind, you have the warmer water coming from the Pacific. Okay, Rebecca Woodgate's work and her team have shown that the halocline is changing. So halocline, of course, is a density gradient or a density transition. And so it's very likely that you're going to have differences in the salinity, especially near the surface, and then differences in temperature as you go further down in the water column, be it at 50, 100, or 150 meters, depending on what is happening due to the changing aspects of the ocean throughout the seasons. In other words, the halocline is constantly changing, and this changing is reflecting the seasonality of what's happening in the Arctic Ocean. So you have that fresher water on top, and that's so you have differences in salinity, and those differences in salinity are especially pronounced when we encounter the warm Atlantic layers. You get the halocline. But as you go down into the warm Atlantic water mass proper itself, you're going to start seeing differences in temperature. And how do these interact with the other water masses nearby? This is not yet well understood. This work is trying to elucidate some of the fine particulars of that. But here's the other thing to keep in mind. The Beaufort Gyre is anticyclonic, or it rotates in a clockwise manner. In the northern hemisphere, such rotations creates what we call a convergence zone in the middle. Well, in a convergence zone, you have downwelling, so that water gets downwelled. Well, we have a thing called conservation of volume. So you have to replace that volume that goes down somehow. And that somehow could very well be this Atlantic water getting entrained into the Gyre, and through the convective processes, it finds itself being upwelled, i.e. going from whatever depth it was to near to the surface. So that means what? As it's getting entrained, the properties has to be changing. It has to either be getting cooler, less salty, or maybe it maintains its, so it has to change its properties, be it in temperature and or salinity, in order to, basically become less dense, buoyant, and start flowing upward. And then as it's flowing upwards, it's diffusing, it's mixing, and so forth. And of course, it's bringing the heat with it. So those are some of the mechanisms that could possibly explain what's happening here. The point of this is that there's recent research that indicates the Beaufort Gyre may be a mechanism that helps push sea ice out through the Fram Strait. The Beaufort Gyre sea ice, the age of the sea ice is declining. It used to be, 4, 5, 6, 7 years would be the norm, sometimes up to 8, 9, 10 years. Well, that's all disappearing so that you're getting younger ice, thinner ice. So it could very well be that incorporating the Atlantic intermediate water, North Atlantic intermediate water, incorporating that into the gyre with its warmer temperatures is contributing to the melting of the ice, to the loss of ice thickness, to the loss of ice volume, and to the loss of the older age ice. So basically, these two aspects, these two physical mechanisms may have a contributing role in one, how sea ice may get pushed out the Fram Strait, keeping in mind with the Arctic Dipole, how its influence on that, but how the ice can go out the Fram Strait, and a mechanism to explaining the decline in multi-year ice. So that to me is the important implications and significance of this work. And obviously more research and data collection will need to be done in order to ascertain if this hypothesis and proposed mechanism works, is valid, and of course, like anything else, may need some little modifications and tweakings. But that's called science. So I find this to be interesting, and I just wanted to quickly share this with you. Until next time. Hello, folks. This is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.